To be sure, a formal axiomatic system such as the Zermelo-Fraenkel axioms is undeniably simpler than the universe, or even a small subset of it, but that leads us to an intriguing conclusion. Any subset of the universe elaborate enough to mimic the operations of the natural numbers will exhibit emergent random behavior not predictable from within that subset of the universe. This means that novel or random supervenient properties will emerge from underlying properties when those subvenient properties are sufficiently scaled up. One potential critique of this conclusion might be that the natural world doesn't exactly replicate the operations of the natural numbers. However, anyone familiar with the sciences knows that nature, in its reductionistic domains, not only mimics the operations of natural numbers, but also embraces the integers, reals, imaginary numbers, differential equations like the Navier-Stokes equations, and much more. Moreover, nature can compute least actions, perform gradient descents, and execute a range of complex mathematical operations, even those yet to be discovered. This remarkable feature of the universe was insightfully explored by Eugene Wigner in his seminal paper, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. Wigner famously stated, "The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve." Even Galileo himself in 1623 observed, "Philosophy is written in this grand book, I mean the universe, which stands continually open to our gaze. But it cannot be understood unless one first learns to comprehend the language and interpret the characters in which it is written. It is written in the language of mathematics, and its characters are triangles, circles, and other geometrical figures, without which it is humanly impossible to understand a single word of it. Without these, one is wandering about in a dark labyrinth." Indeed, the deeper we delve into the workings of the universe, the more it resembles a sophisticated computational system. One critique raised by Wolfram regarding Gödel's theorems and its implications here is that these theorems rely on a human concept of truth that may not necessarily apply to the larger universe. While this is a valid observation in the strict sense, since Gödelian numbering requires a true proposition to be shown unprovable within the formal system, it's important to recognize that all of mathematics is grounded in our notion of obvious truth in the form of axioms. Without axioms, mathematical systems would collapse into an endless regress of nested definitions. Moreover, several other undecidability theorems, logically equivalent to Gödel's work, have been proven within different and unrelated systems. Finally, if our conception of truth were fundamentally flawed, we would expect observable consequences. Yet the continued success of reductionism, in its ability to predict and explain natural phenomena, suggests that such consequences have not materialized. Consider the intriguing concept of busy beavers in the realm of Turing machine computability. The busy beaver problem asks, for a Turing machine with a fixed number of rules, what is the maximum number of steps it can take before halting on an empty input? Ignoring programs that run indefinitely, the focus is on those that eventually halt. The number of steps taken by an n-rule busy beaver grows faster than any computable function, and is itself an uncomputable function. And notably, the computer scientist Scott Aaronson has constructed a busy beaver that encodes the Zermelo-Fraenkel axioms and systematically constructs a proof of every possible theorem. In this framework, truth is both rigorously defined and computable. Aaronson programmed this busy beaver in such a way that if it ever finds a contradiction in a proof, it will halt. However, because halting would imply the inconsistency of the Zermelo-Fraenkel axioms, an outcome we know to be impossible, it can never halt. Remarkably, this Turing machine and busy beaver program could theoretically be implemented in a physical system, such as an adiabatic computer. Such a construction would underscore the profound interplay between physical reality and foundational notions of truth, computability, and provability, demonstrating how abstract mathematical principles can manifest in tangible systems. In essence, our notion of truth is equivalent to causality. A state B is said to be true if it naturally follows from the causal application of a computational rule or physical process to a previous state A. In this sense, the universe is calculating true theorems through its ever-evolving dynamics, and our brains have learned to apprehend this notion of truth during the course of our evolution. Consequently, in this universe, our notion of truth is indeed universal. To be sure, this definition of truth need not hold in other universes built upon logical foundations wholly different from the laws of causality. Despite this definition of truth in terms of causality, the explanation of the cause disappears at higher levels of scale because of Gödelian randomness. However, within the slices of reductionism, this causal implication of truth holds. This will be elaborated further in Chapter 11.